Okay, so we'll be looking at DOF, degrees of freedom analysis for a distillation column. So we'll be looking at it for condenser. We added this split here that brings out the distillation and or the collection for the distillation and sends the what's not collected back through. We have the rectifying, the feed, the stripping, and the reboiler. And the first thing we'll be looking at is one of our equilibrium stages here, just to start out. We have our liquid coming through here and our vapor going up, and we have this heat exchange right here, Q. So first thing that you want to look at for a degree of freedom analysis is your variables. So we have a temperature variable, we have a pressure variable, we have a heat flow variable, and we want to look at the number of components we have, and we also have a temperature and pressure for each of those for our streams. So we have temperature and pressure for each of our streams, and we also have a number of components that will be in each one of our streams, and that's will be our total number of variables. So we can then plug this in here. So our degree of freedom is going to be our number of variables minus our number of equations that we'll have. So we'll have 4c plus 2 plus 3 in brackets here, and then we'll subtract that by number of variables. So our number of variables for this equilibrium stage, we're going to have a mass balance for each of the components that we have, and we're also going to have a VLE diagram for each of the components that we have, which is going to involve our stripping or our VLE. So it's going to be called our equilibrium factors with all those. We'll have an energy balance. We'll just have one of those for our whole system, or for just this box right here where we separate our boundary at, and we'll have a temperature and pressure equality for each stream. So every time this leaves and this leaves, our temperature and pressure for that stream have to equal our temperature and pressure for that stage that it's leaving from. So, and that's going to have that's going to be dependent on how many streams there are, because we have 2 streams leaving. We'll times that by 2. So we can go ahead and plug that into the equation. So we'll have 4, and we'll have 5 and 2c. So we'll have 2c plus 5. And then we can go ahead and combine these two. So we'll have 8c plus 2 plus 3 minus 2c minus 5. And we'll be left with 6c, 5, and wait, that should be 8. Or it should be 4c plus 8. There we go. So we have 4c minus 2c, so we have 2c, and then we have 11, and 11 minus 5 equals 6, so we have 2c minus 6, and this will be the degree of freedom for our equilibrium stage. So we'll move on to the next one that we can do degree of freedom on. Also, this degree of freedom just basically tells us how much wiggle room we have with our system, and how many factors we can have control over. So if we have, like, let's say 5, we can have control over 5 variables here, or factors, and past that we can't control one. So you kind of have to pick and choose which 5 you want to control, and the other ones involved will be dependent on those, and you'll have no control over. So this is why the degree of freedom analysis is important. Also, this should be plus 6 because there's 11 over here. So 2c plus 6. Okay, so the next one that we can do is the feed stage. So our feed stage is going to be right here. I forgot to add in our arrow right here. So the only difference between our equilibrium stage and our feed stage is our feed line coming in through here. And we discussed earlier how well, these right here, these two are going to be our dependent on the number of streams that we have for these variables, which is why we have the c plus 2. We have 4 streams in our equilibrium here, so we times our c plus 2 by 4. So what we can do for this is we can add our c plus 2 right here, and we can then get our answer of our feed. So our feed degrees of freedom, since we just add one stream, it's just going to be 2 or 3c plus 8. So 3c plus 8. So this is our feed, and this will be our equilibrium degree of freedom. So they just add one stream there. So we'll move on to the reboiler next, where we lose a couple streams. For our reboiler, we lose our we don't have a liquid stream coming in here, or we don't have a vapor stream coming in here, so we lose one of our streams that we had. So if we go back to our equilibrium, based off that, we have our 2c plus 6 right here, and since we lose one of these, we can just subtract our 2 or our c. You can subtract a c plus 2 from here. So our reboiler will be equal to, for our degree of freedom, will be equal to our c plus 4, and that will be our degree of freedom for our reboiler, since we have an absence of our vapor coming in. So so just to go over it again real quick. So our variables are our temperature of our whole system, our pressure of our whole system, our heat flow of our system. Then we go into the number of components that we have, and this is going to be dependent, or these are going to be multiplied by how many streams there are coming into, and then we have a temperature and pressure for each stream. And since we have a temperature and pressure, this is going to be a 2. We're going to times it by 4. We have our mass balance, our VLE, our energy balance, and our VLE and mass balance is going to be based off of how many components we have. Our energy balance is going to be based off the whole system, and then again we have our T and P equality that come in to play here by leaving our 2 vapor streams leaving, or our vapor and liquid stream leaving, which is our T and P here have to be equal to what stage they are leaving from. So we can then use these to plug it into the DOF equation. So the next thing we'll be moving on to is, okay, so the next thing we'll be going over is the condenser here. So this one is a little bit different. So if we look at our variables and equations we had laid out for our equilibrium here, there are 2 changes that we'll add here. One being that our TP equality is going to be different. We're only going to have one stream leaving, so we can only have one TP equality, and our VLE is going to be gone. We don't have another component there. We don't have an equation here because our condenser is forcing our vapor that comes up to turn all to a liquid. So there's no vapor liquid equilibrium there. And then number of streams is going to go down to 2. So it's just going to be 2 c plus 6 minus, and then we have one stream here, so 2, 3, so c plus 3. So then you're left with c plus 3 right here, and this will be our degree of freedom for our condenser. Actually, oops, I forgot one thing. So we only have 2 streams coming out of our in our condenser. So right here, this is only going to be 2, so it's going to be 2c plus 2 plus 3. So 2c plus 2 plus 3, and then minus. So if you were to distribute that out, you have 2c plus 4, so that'd be 7. So then you have 2c plus 7 minus the c, so you're left with c, and you have 7 minus 3, which is going to be 4, so you have c plus 4. So c plus 4 is going to be your degree of freedom for the condenser. Okay, so now we'll move on to the splitter. We'll go back and look at our variables. So these will all stay the same right here. Our VLE again will not be there because we're not having any exchange there. It's still our condensed liquid. And we'll have all this will stay the same, and then we'll add the two things that we'll add will be a ratio variable, which is how much of our distillate right here is leaving, and then we can add a ratio equation over here, which is going to be our ratio times our component pretty much, which is just going to be a simple mole balance of how much is leaving and how much is staying in the system compared to our total number of starting moles that the component started as. So we'll add a C right here because that is dependent on how many components there are. So we have our ratio, and which is just as 1, and we have our ratio times our component, which is based on how many components we have, and then we only have 3 streams, so we'll times this C plus 2 by 3. So we'll have 3 times C plus 2, and then we'll have 1, 2, 3, and then plus 1, so 4 for our ratio variable that we'll add. And then this will be minus our, so we'll have 2C because we got rid of the VLE but added that, so we'll have 2C. And then we will have 2 exiting streams again, so that'll be 2. So, or we'll have 2 exiting streams again for our TP quality, so times this by 2, so I'll have 4, and we'll still have our energy balance here for that boundary, so that'll be 5. So that should be 5. Okay, so you're left with 3C plus 6 plus 4 minus 2C plus minus 5. So you're left with C plus 5 for the degrees of freedom for our splitter. Okay, so for our so next we'll be working with our scripting section or rectifying section. We can just treat as 1 here. So we're gonna be working basically with our equilibrium that we defined here, since like each one of these kind of blocks right here are equilibrium or individual or equilibrium that we calculated before. So and also we'll have to add our number of stages n as one of our variables that we'll have. So n is going to be our number of stages, which is going to count for 1. And then since each one of these is basically an equilibrium block, we can do n equals 2c plus 6, since the 2c plus 6 is what our DOF was that we calculated for our equilibrium section was. So we have that, and then but we can see here that we have streams that are coming in and out that are crossing our boundary here, so we have to take that into account. So we have 2 streams for every block here, and we want n minus 1 because we don't want to take one of the stages into account because we still want those streams. And then there's going to be C plus 2 here for every, so we want to take in the n minus 1, and then we want the C plus 2, which is the number of dependent on streams right here. So how we times this by 4, C plus 2 every time. Our C plus 2 is kind of the part of the equation that is dependent on the number of streams that there are. So we want to include that here, and then we can go ahead and add these together, and we'll get 2nc plus 6n minus 2 nc minus c plus 2n. And then we want to, so nc minus c, wait, two nc plus 2 and minus c minus 2. Okay, and then we have 2 NC, 2 NC, so those cancel. And you're left with plus 6N minus 4N, so you have 2N, and then minus 2C, or plus 2C, and then plus 4. And then plus 1 because we had added that, so you're left with 2N plus 2C plus 5. And this will be your degree of freedom for what section you want. Okay, so I have all the ones that we've derived, and we can go ahead and add them all up now. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 10C, and then plus 2NR plus 2NS, and then 9, 14, 22, 27, and 31. So this will be our total right here, except that we have, we're counting streams again that aren't exiting our whole system here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 streams that we've counted that are not a part of our system. So we have 9C plus 2. We'll do the same thing we did last time, and we'll go ahead and subtract those out. So we'll be left with C plus 2NR plus 2NS plus 18 once this is distributed out, and this will be our total DOF of our distillation. Okay, so the next thing to go over are the common specifications that we have with the distillation column. So the first one we'll specify in the rectifying and our rectifying and our stripping section. We'll define that Q is adiabatic 0, and we'll have pressure defined. So that will take out our degree of freedom in our rectifying and our stripping section. So that'll take out our 2NR and 2NS because we have 2 and 2 here, or 1 and 1. Okay, and the next thing that we can look at is we'll have our feed temperature, our feed pressure defined. So that'll take out that C plus 2 that we were using before. That was dependent, that we would use to show the degree of freedom for each stream. So if we define feed T and feed P here, our C plus 2 will be gone. So we'll cancel out our C here, and this will go down to 11. So if we define we'll define our feed Q and our feed P for the system, and that'll take our degree of freedom down to 9. And then we'll have the number of stages in the rectifying and split, or our rectifying and our rectifying, both our sections. So that'll bring it down to 7. And then our condenser, splitter, and rib oil pressure will also be defined. So that'll bring it down to 4. And then our splitter is adiabatic, we'll say. So that'll go down to our 3. And our reflux and our distillate, how much is leaving there is defined. So that'll bring it down to 1. And then we have our condenser product will be at a saturated temperature, and that'll bring it down to 0. And so we have 0 degrees of freedom left, and this is the most basic assumptions and specifications that will be met when dealing with a distillation column.